So I think we can start. So yeah, welcome to the session of the papers. So I'm Paolo. We start the first paper presented by Junjie Luo from Kyushu University in Japan. And the title is A Comprehensive Study of Bug Fixes in Quantum Programming. So you have 15 minutes, then you have 5 minutes for question. And yeah, the audience, you can just unmute yourself and maybe you raise your hand before and just ask the question. Okay, please, the stage is yours.
Okay, thank you. Hello, everybody. My name is Junjie from Pangu Research Group at Kyushu University. The title of my presentation is A Comprehensive Study of Bug Physics in Quantum Programs. My presentation is in 6 parts, including quantum computing and quantum programming, research motivation and research questions, methodology, empirical results, future work, and concluding remarks. Quantum computing is a type of computation that harnesses the collective properties of quantum states, such as superposition, interference, and entanglement to perform calculations. The devices that perform quantum computations are known as quantum computers. As we know, quantum computers promise to solve certain computational tasks exponentially faster than classical computers. Quantum computing is fundamentally different from other means of computing and requires the development of specific programming languages and compilation techniques. Quantum programming development is the process of designing and constructing quantum programs to achieve a specific computational result. Nowadays, many kinds of quantum programming languages has been developed for the development of quantum programs. For example, Qiskit, Cirq, Q#, and ProjectQ. As our research motivation, software defects significantly impact the economy, security, and quality of life, yet relying on manual diagnosis and repair of software bugs consumes significant time and money. However, despite their importance, program debugging and software testing have received little attention in the quantum programming paradigm. Although several approaches have been proposed for debugging and testing quantum software recently, no research work have been focused on bug fixing in quantum programs. Our study is driven by the following research questions. Does this bug only occur in quantum programs? Where is the location of the bugs in the programs? How complex to fix bugs in quantum programs, and what type of files were modified in the process of fixing the bugs? And the last one is, what are the bug patterns in the quantum programs? Then we will introduce our methodology. This picture shows the question and analysis process. The first thing we have to do is to determine the target bugs. In order to collect as many bugs as possible, we collected bugs generated in the most commonly used quantum programming languages, including Qiskit, Cirq, Q#, and ProjectQ. We collected bugs raised on GitHub, Stack Overflow, and Stack Exchange in terms of platform for reporting bugs. We manually collect bugs for each target language on different platforms, since the number of bugs in quantum languages is not very large, and we need to filter the bugs to find those that meet our requirements. There are 3 filter conditions for bugs as follows. First, we have to select the bugs that are related to quantum programs. If a bug is in a program that does not involve any quantum computation or operation, then the bug will not be included into the question. Then the programs we select should be written by developers, which means that the bugs that occur in the quantum programming languages itself will not be discussed in this study. Finally, as a rather important point, we require our filter data to have pre- and post-fixing code. We need to confirm that the changes are effective by reading the feedback from the users who raised the bugs. According to our method, we collected a total of 197 samples to be filtered in the first step and 96 samples to be analyzed by filtering the samples in the second step. In the last phase, we analyze all the valid data collected. We count the distribution of bugs for different research questions, focus on some representative examples, and finally give our findings. And in this part, we will show our empirical results in our study. The first research question investigates the proportion of classical bugs and quantum-specific bugs in quantum software. Generally, quantum-specific bugs are different from classical software bugs, as repairing them requires the domain knowledge of quantum-related concepts, properties, computational formulas, and quantum programming languages. Table 2 shows the statistic of the number of classical and quantum-specific bugs in the data we collected. From the results of the investigation, we can derive the following findings. Clearly, the number of quantum-specific bugs is much greater than the number of classical bugs. From this finding, we can learn that since more of the existing bug fixing approaches focus on classical programs, it will be a great challenge to deal with the bugs in quantum programs. And it also means that the researching bugs fixing in quantum programs is highly worthwhile. The second research question investigates whether files other than the source files were modified during the fixing of the quantum programs, and the number of lines of code that need to be modified to fix each bug in the quantum programs. Here we give finding 2 directly. In all the bugs we collected, only the source file has been modified. And this figure shows the statistic of the number of lines needed to be fixed classical bugs and quantum-specific bugs in quantum programs. And thus, we have the finding 3. More than 70% of the bugs in our collection of quantum programs can be fixed by modifying only 1 line of code, while less than 10% of the code requires modifying more than 6 lines. This implies that the cost of fixing bugs is generally low in existing quantum programs. The third research question explores the difficulty of fixing bugs that occur in quantum programs. Here, we refer to the 4 levels of fault complexity proposed by Zheng and Su. A single repair action, non-data dependent repair actions, data-dependent repair actions, and mixture repair actions. This picture shows the distribution of complexity, and we can catch finding 4. Since single lines fixed are directly classified into C1 complexity, the proportion of C1 complexity is much higher than the other 3 complexity levels in quantum programs. This reflects that the complexity of bugs in current quantum programs is generally low, but there is still some bugs that are difficult to fix. And all the bugs in this part belong to quantum-specific bugs, and thus the difficulty in bug fixing cannot be ignored. In the 4th research question, we count the file types of all modified files. The filter shows the statistical results of our study. In our collected samples, the most frequently modified source files are Python source files, and there are also a few Q# and C# source files. This is in line with our expectation, as we know from finding 1, and that only source files were modified in the process of bug fixing in the data we collected. In the last research question, we analyzed and counted the bug patterns of the 96 valid samples collected. In our study, we divided the bug pattern into 4 major categories: API-related, incorrect application logic, math-related, and others, and also detailed 0 subcategories under each major category. Next, I will introduce each bug pattern separately. The API-related bug pattern means that the error is caused by an API in quantum programs. There are two main subcategories, including API misuse and outdated API keyland. The incorrect application logic bug pattern is the bug state caused by errors in the implementation of the application logic when writing a quantum program. This bug pattern consists of 6 subcategories. Immediate representation refers to wrong program elements, incorrect scheduling, wrong declaration, wrong way of implementation, and qubit-related bugs. In our study, if the developers make an arithmetic mistake, it will be categorized into a math-related bug pattern. And math-related bugs can be divided into 2 subcategories: incorrect numerical computations and incorrect randomness handling. In addition to the 3 main types of bug pattern mentioned above, there are some other patterns included in our study, which include a misconfiguration, type problem, type probe, and overflow error. Based on the results of the analysis of the bug patterns, we have finding 6 and finding 7. Based on the table 3, we can find that overall, the statistic shows that in the existing quantum programs, programmers' bugs are mainly focused on API-related bugs and math-related bugs. This means that the programmers are still not proficient in the use of a quantum programming language in the development of quantum programs and have difficulties in qubit algorithm and operations. At the same time, it should be the focus of the following bug-fixing related work. Consistent with the above finding, quantum-specific bugs are mainly concentrated in API-related and math-related bug patterns. Classical bugs, on the other hand, are smaller in total and evenly distributed across bug patterns. This means that in the study of bug fixing in quantum programs, researchers still need to pay extensive attention to the bugs that occur in classical programs. The high percentage of quantum-specific bugs in API-related and math-related bugs patterns also indicates that the current bug-fixing efforts are difficult to be applied directly to quantum programs, and further research is needed in this area. As guidance for future research, the results can provide insights into how to develop and improve the bug-fixing method for existing quantum programs. For example, what knowledge is needed to repair quantum programs and whether this knowledge is included in classical program fixing methods. In addition, the results also shows the potential regarding the application of existing automatic fixing methods in quantum programs. Also, the results can provide a clear direction for the study of quantum programs bugs. For example, the results show some bug pattern in quantum programs and analyze the frequency of each bug pattern. Based on these patterns that we have summarized, our future work can propose new methods for locating quantum-specific bugs as well as developing static analysis tools. Thank you.
Yep, thank you for the nice talk. So are there any questions? If you have any, you can directly unmute yourself, and maybe I can start with one. So for the bug patterns, so
yes,
are these, I mean, I can imagine that I can have similar patterns for normal code. So my question is that if the frequency of these patterns is specific to quantum, I mean, if quantum program produces more faults of more bugs of one particular type rather than normal program. Because at first, when I say related, I was thinking, okay, but API related are common also to normal programs. So my question, what's in the quantum that, so yeah, so which of these pattern is more affected by the quantum?
Do you mean that we should we classify the quantum specific bugs into dependent bug patterns?
So if I take the same patterns also for normal code, would I find a different distribution, or more or less the distribution is similar in normal code?
In fact, yes.
Okay, yeah, that's.
In fact, we have classified them in quantum specific and classical bugs in our bug patterns phrase, and we can find that there's a huge difference between the classical bugs and quantum specific bugs.
Okay. Yeah, okay, maybe we can take offline. Yeah, but
I think Wolfgang has hand raised.
Actually, Stephanie, my co-author, but we share one Zoom session.
Hello, thank you for the interesting talk. I wonder how many of the bugs in the quantum specific code are still due to developers learning the new technology, and whether experienced developers have different bug patterns or bug frequencies than junior developers. Have you looked at this, or are you planning to look into this? It's a very new technology, right? So people have to learn how to use it, and when they are learning, they make more mistakes. I wonder whether experienced quantum software engineers make fewer mistakes than unexperienced quantum software engineers.
I think I will try to answer this question, and I think we can try to collect these quantum specific bugs and find the same points in them, and we can summarize some knowledge from them and use them to the future research. I think.
All right, thank you.
I think I have a follow-up to that. It's actually a question, then maybe becomes a suggestion. But were you folks extracting the bugs and counting them, or you also looking inside to see what exactly the bugs were or where they were happening?
We have checked what the bugs exactly.
Okay, because my question actually is, did you notice any patterns into how, if bugs co-occur? So for example, you mentioned that API related and math related are the most occurrent, ones that occur the most. Is there any pattern as such? For example, they tend to occur together. So they tend, the bugs, if you're observing a file, maybe you actually have a math related together with an API related. So maybe the developer fixed something on the mathematical implementation, then that results in a change in the API as well. So there are two bugs associated. Sometimes these co-occurring bugs are also a thing in other types of systems.
In fact, if these two kinds of bugs appear in in one programs, and we will statistic it into 2 bugs, and it means that in one quantum programs there is API related bugs and math related bugs. There's 2 bugs.
Yeah. So you haven't looked into bugs that may be related to each other. So bugs that are associated. They're different bugs, but they are associated. So maybe one leads to another fixing.
Yes.
Okay. No, yeah, this was, I think this is something actually, for me, it sounds like a follow-up to that, to actually explore even more to see how the bugs appear and they are fixed. But yeah, thanks a lot. It was a very interesting talk.
Okay, thank you.
Thank you. Thank you, Junjie. We can go to the next talk.